the two things you need to have open are your notes package to the lesson on graphing, okay, and to have open as well the Google Sheet that I posted in the stream this morning. It's like graphing practice or something like that is what I called it. Okay, you can have that open as well. What we're going to do is look at what graphs are for, get a couple built, maybe get some calculations done with them, and then we'll continue on with that on Monday because it's a short class today, okay, and we probably won't get it all finished. And that'll be moving towards doing our lab on position versus time graphs on Tuesday. All right, so we're doing a fair amount of graphing here over the next little while. How many people are in Math 10 right now? Okay, wow. Usually there's a few more hands than that. Are you on to graphing? Yeah, okay, so you're getting it. You're getting a double dose over here, so you'll be really good at it. All right. So what's the purpose of a graph? Why do we use graphs? Yeah, to show the relationship between different data sets. Okay, most of the time it's between the manipulated variable and the responding variable. So the responding variable always goes on the y-axis, and the manipulated variable always goes on the x-axis. And that way we can see the relationship between our manipulation and whatever it was we were watching in the experiment. A graph is a quick visual reference to an experiment, okay, or a relationship. And so we can quickly tell what's going on without having to look at a bunch of numbers in a table. Okay? Because numbers in a table doesn't, I mean, we can get a relationship from that, but it's not as kind of visually obvious or as quick, right? Looking at this graph right now, can I tell pretty quickly what's going on in this experiment? Okay, so I look, and there's a title, and it says temperature versus photosynthesis. So right away I know this is an experiment about plants and the effect that temperature has on their rate of photosynthesis. If I look a little bit closer, I can see that temperature was the manipulated variable. Okay, so that means that in this experiment they probably had different plants at different temperatures. Okay, and that on the y-axis is the rate of photosynthesis. Now that part's not great. What's not great about the y-axis? Here we have temperature in degrees Celsius, and here we just have rate of photosynthesis. What's missing from that axis that would be helpful?
The units?
Yeah, there's no units. I have no idea. Is 100 good? I don't know. 400 what? Elephants? Oranges? Old ladies with walkers? Like, I don't know. It's completely meaningless without any units. Okay? All I can tell from this graph is it goes up until it gets to about 30 degrees, and then it falls right off. All right, so that's, can I tell that pretty quickly though? Like, did it take me very long to figure out what happened in this experiment? Other than the one stumbling block of there's no units for rate of photosynthesis. That's probably, I would imagine, like milligrams of oxygen per minute or something like that. They probably would have had to measure how much oxygen the plant put out, okay, as a rate of photosynthesis. But in the end, it doesn't really matter. I can see that temperature does have an effect on the rate of photosynthesis. And that effect is that it goes up and then drops off really quickly after 30 degrees Celsius. Okay? Could I have gotten that data as quickly from 2 rows of numbers? Probably not. Okay? This was quick. I could tell what was going on here. And that's the purpose of the graph. Okay? All right, so when you build a graph, obviously you're going to have to put labels on each axis and things like that. Okay? We want to build it so that it looks useful. Right? So I'm going to walk you through this first graph, and then we're going to do a couple of calculations for it. So if you can scroll along there in Google Sheets until you find the one that's about book thickness, okay? I will find it here on mine and walk you through it. Okay, So first one's diameter and circumference, book thickness, that's the one we're looking for, right? Okay, so if everyone can have this sheet open on their Chromebook and just kind of follow along with me so that you can see how we get this line graph built properly. Okay, so I'm going to put my pointer in the first cell, so cell A1, where it says number of sheets. I'm going to click and drag, so click and hold until you've highlighted all of the data. Let me know if I'm going too fast. Okay, then I'm going to go up to Insert, and I'm going to pick from the drop-down menu Chart. Okay, so right here. Click on that. Okay, and it's already built a bit of a graph here for me. All right, because I had this stuff here, I had like labels already for what data was in those columns, it automatically built that into my graph. Okay, so if you do that when you're building a graph, it saves you time when Google Sheets makes the graph for you. It knows what to label each axis. All right, and it built a scatter chart. Sometimes Google picks the wrong kind of graph. If you put certain data in, it picks the wrong kind. And then you just have to go here to Chart Type over here on the right and just click on the drop-down menu and you scroll down. Come on, scroll down. Until you get to Scatter, click on it, and only if it picks the wrong graph. Obviously, in this case, it picked the right graph. Okay, so it says here on the x-axis we have number of sheets, and in the y-axis thickness in millimeters. All right, because as I add sheets to a book, it's going to get thicker. Yeah.
Diameter and circumference.
Yeah, you have to scroll ahead. It's not the first. See right down here? You have circles graph here on the bottom. Circles graph, rubber band, book thickness.
I don't see it. Look down the bottom. Oh, okay.
Okay, so now that I've got that, okay, the graph still isn't finished. Right? There's still a couple of things I need to do from the Customize menu over here on the far right. Okay, so I want to click on Customize, and one of your options is Chart Style. We don't really need to do much with that. That's where you pick what font it is and what the background color and what the lines color are. Like, I almost never go in there. Okay, Chart Axis and Titles is where you would go to change things like the title here, which, I mean, it's okay. It tells us what's on the graph. Okay, or the horizontal axis title, which is also okay. It's number of sheets. Okay, and vertical axis title, it's okay. It says thickness in millimeters. So I don't actually need to change any of that either. In series, I do need to do a couple of things. So I want to click on the drop down here for series. Okay, so it says there's only one data set and it's thickness and it's using blue dots. Okay, you can change the color of those dots to anything you want. If you don't like blue, you can make it magenta or whatever. Okay, and you can change the size of those points. And I'll often do that just because when you have points this big, it's kind of misleading as to where they are. So I often make them like 2 pixels, just so they're a bit smaller. Okay, so all I did here was go point size and I picked 2 pixels. Right? You can also change what shape those points are if you want. That's especially useful if you have more than one data set. Okay? Sometimes it's helpful to use a different color and a different shape for the points. We only have one set of data here, so we'll leave it as circles. Okay? And here at the bottom, you have 3 check boxes, and one of them is for trend line. Click that box, and Google Sheets will draw a line of best fit. Okay? That line represents the trend or average of the points. In this case, it goes directly through every single point because this is a perfectly linear relationship. Every page is the same thickness, so adding pages always changes the thickness by exactly the same amount. Okay? All right. When you click on that, you'll notice that you get more options down below. Okay? You want a linear line, it picked the right one. The relationship was linear, but your options are exponential, polynomial, logarithmic, power series, and moving average. We'll only ever use linear. Sorry, I clicked out of my chart editor. Sorry, just gotta get back here. Series. Okay. So that stuff I'm not going to change, but I am going to go down here to label. Okay, and I'm going to click on that where it says none, and I'm going to use equation. Okay, and you can see that when I do that, I get this little extra tab up here on the top of my graph. That is the equation for our line. Y equals m times x plus b. Okay, so they just don't have the y equals there, but okay, that's what this equation is right here. All right, at that point, the graph is built. I don't have to do anything else to it. Now I went pretty slow. Could you build a graph pretty quickly? Okay, like really quickly. Highlight the data, insert, chart, bang, 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 it's done. Okay, like you can literally have a line graph built in a couple of minutes, okay, with Google Sheets, which is so much better than the way we used to do it, which is get a piece of graph paper, okay, look at what the biggest number you have is, figure out what each line on the graph paper should be worth, draw the scale on by hand, okay, and then plot all the points by hand, and then use a ruler to draw the best bit line on. Doing what we just did in 5 minutes used to take 25 minutes to a half an hour for one graph. Okay? And it was never as accurate as what this does, because this just uses an algorithm to draw the line for us. Okay? If I had everybody do this by hand, everybody's line would be just a little bit different. Okay? Because everybody puts that ruler on there just a little differently. Okay? So this is a much better way to do it, plus it's faster, clearer, easier. Okay, so it's all good for us. Okay, everybody good with having that graph built? Okay, so we're going to go back here and we're going to look at some of the things we can do with that graph. Okay, so this is our book thickness graph. Okay, so yours looks probably just like that. Okay, and what we want to do is we want to calculate a few things using the equation that the line gave us. Okay, so here's how this equation works. Y stands for any y value of a point on the line. Okay? M is the slope of the line. Okay? In this case, the slope of this line is 0.15 millimeters per sheet. In other words, it tells me the thickness of one sheet in the book. Okay? And every time I add one more sheet, the book gets thicker by that amount. And that's why that line goes perfectly linear through every single point on the graph. Okay? Because every sheet I add will change the thickness of the book by exactly the same amount. Okay? Now, x is the x value for any point on the line. So the x value for, let's say, this point right here would be 50. The y value for this point would be, I should pick the right point, third, 12 and a half, like that. Okay, everybody with me there? Okay, and then finally, we have b. B is our y-intercept. It's where the line crosses the y-axis, or it's what y is when x is 0. So, in this context, this is a book that has no what? No pages. But it's already 5 millimeters thick. What do you suppose that is? The cover. Okay, so the y-intercept in this case is telling me the thickness of a book that has no pages. Okay, it's what y is when x is 0. Okay, so in other words, it would be the cover. okay, the thickness of the cover. And then from there, the book would get 0.15 millimeters thicker every time I added a page. Okay. Everybody all right with that idea? Right, so that's what we can get just by looking at a graph. We haven't done any math. We've just looked at the graph and interpreted what's on the graph. Okay? That's going to be an important skill that you're going to be required to show in this course. I give you a graph and I ask you to do some interpretation. The interpretation doesn't involve any math. It just involves understanding that in this relationship, more pages means a thicker book. Okay? And that the pages are 0.15 millimeters thick, and that the cover is 5 millimeters thick. That's what I can get without doing any math. Okay. Now, the first thing they want us to do here is calculate the number of sheets in a book that is 80 millimeters thick. I can do that with this equation. Okay? Now, they gave me the thickness of the book. So did they give me an X value or a Y value with that number?
A Y value.
A Y value. How do I know that?
Because it's on, the thickness is on the y-axis.
Exactly. Thickness is on the y-axis. So this is a Y value. And they want to know the number of sheets, which is an X value. So in this case, they want me to solve for X when Y is 80. Okay, everyone follow what I'm doing here? All right, so I know that for this graph, y equals 0.15 times x plus 5. Okay, I want to solve for x. So I need to get x by itself. Do I have to do a little bit of algebra? Okay, what should I move first? I've got to move the 5. It's not attached to x. Okay, that's the first or the third rule of algebra, right? Move what's not attached first. Okay, right now I'm adding the 5. So if I want to move it, I need to subtract the 5. Okay, so I'm going to have then y minus 5 equals m times x. Okay, sorry, the point, so I should put in the numbers. I was doing this all with numbers. I should continue that trend. Okay, I want to get x by itself. What do I do with the 0.15? Divide it. I do the opposite. Right now I'm multiplying 0.15 times x. If I want to move to the other side, I perform the opposite operation. Okay, so I'm going to move that over here. Okay, am I solving for x? Definitely. Okay. Only thing I have to be careful of now is how I punch this into my calculator. If I just punch it in a line, it will do order of operations and give me the wrong answer. Okay, because it will divide 5 by 0.15 and then subtract that from y, because that's what it's programmed to do. I don't want it to do that. I want to do the top and then divide by the bottom. Okay, whenever you manipulate something, that's something you have to keep in mind. Okay, so if I'm going to perform this calculation then, okay, we were told y was 80. Okay, so we're going to have 80 minus 5, so we're going to have 75 on the top divided by 0.15. Okay, so 75, 80 minus 5 divided by 0.15. Okay, so that book will be 500 pages. Okay, everybody all right with what I did there? All right, now remember I said you have to do the top and then divide by the bottom. If you put it all in a line, you don't get the same number, right? Because your calculator does order of operations and you don't want it to do that. Right? So make sure you do it in the order you manipulate. Okay, see if you guys can solve number 2. You're looking for the thickness of a book that has 805 pages. So first thing I've got to ask myself is, what part of y equals m times x plus b am I looking for? I'm obviously not looking for m, because I already had it. I'm obviously not looking for b, because I already had it. Okay, so am I looking for y or x? Y, because y is on, or sorry, because thickness is on the y-axis. They want me to calculate a thickness for a particular x value. They told me x equals 805 pages, okay, or sheets. So, now, do I have to manipulate this at all, or can I just plug in? I can just plug in, it's already solving for y, okay, so this one's even easier than the first one. So I'm just going to go y equals 0.15, because that's m, times the x value they gave me, 805 pages, plus 5. Okay, that's the 5 millimeters I'll be covering. Okay, so 0.15 times 805 plus 5. Okay, so that book is going to be 125.75 millimeters thick. Everybody all right with that? Okay, the last question is, what's the number of millimeters per sheet? Do you have to do any calculating for that one? What's the number of millimeters per sheet? 0.15. Okay, now here's how I know that. M is what we call the slope, and it's probably the most important piece of information on a graph because it tells us the rate at which y changes as a function of x. Okay, so in this case, they're telling us every time x goes up by 1, the book gets 0.15 millimeters thicker. Okay, so if I manipulate this equation here, okay, to solve for m, I would first move b, just like we did before. Okay, so I would have y minus b equals m times x. And if I want to get m by itself, what do I do with x? Divide. Okay, so I'm going to divide both sides by x. X is going to come over here. So m tells us how much y changes over x. Because what we're really doing is taking y, subtracting b, and dividing it by x. In other words, it's the rise divided by the run, if anyone's ever heard it described that way. Okay? It's the rate at which y changes over x. Okay? In this case, it's the number of millimeters per sheet. Questions on that one? Okay. Indicator diesel. Good. All right. I want you to go back now to the circumference graph. Okay. So what we have in our data is diameter and circumference. Okay. And we want to plot a graph of that. Okay. Now, before you start, I want a prediction here. What's the relationship between diameter and circumference?
How, like the circumference changes how big the diameter is.
Or, yeah, or vice versa. Okay? If we increase the diameter of a circle, its circumference gets bigger. Yes? How many times bigger is the circumference than the diameter always? There's a number you always put in there.
Is it 3.14?
Yeah, what do we call that number?
Pi.
Pi. What should our slope be for this graph? Yeah, it better be pi. Okay, and it better be 3.14 because that is how much the circumference goes up every time you increase the diameter. Okay, all right. Plot that graph. I'll give you a few minutes to plot the graph, then I'll plot it. Okay, to see how much you remember about plotting graphs. So we click and drag and highlight all the data. Then we go to Insert, Chart. It spit out the right kind of chart. All the labels are good. Okay, so I'm just going to go straight over to Customize, to Series. I'm going to make the points 2 pixels. And then I'm going to put a trend line on. And then I'm going to put the equation on there. And now I'm done. Okay, like you can literally build that graph in under 30 seconds. Okay, probably under 20 if you're really trying hard. Okay, so now that we've got that graph, look what our slope ended up being. Okay, 3.1, it rounds off. Okay, it doesn't actually put in all of the data, but I would imagine it's 3.14 something something. Okay, in there. All right, so let's go back to this. Okay, so when we've got that graph built, okay, it's 3.14 and my y-intercept, okay, that is, what's the value of y when x is 0? Theoretically, what's the circumference of a circle with a diameter of 0? You're all right, you're all thinking it. Say it. 0. You can't have a circle without a diameter. Okay? Now, what is this saying the circumference of a circle is if it has no diameter? It's saying it's 1.52 times 10 to the minus 5. To give you an idea, that is 0.1, 2, 3, 4. Is that experimental error / round off? It is. Okay, that's all that is. It rounded off pi to probably about 3 or 4 decimal places when pi is an unending infinite number. Okay, and that's why it got a y-intercept. That y-intercept should be what? What's the circumference of a circle with no diameter? 0. That the y-intercept for this graph should be 0. But because Google Sheets doesn't hold all of the decimal places for pi, because it would, trip out, because it would just have too many decimals, it goes on forever. Okay? It's actually saying there is a circumference. There really isn't. That's just a rounding error. Okay? All right. So we want to find the circumference of a circle with a diameter of 0.88. Okay. So what did they give me? X or Y? They give me x and want me to find y. So can I plug that into this equation then? Y equals m times x plus b and say, all right, I'm looking for y. M is 3.14. X is 8.88 plus this number here. Okay, would that get me my circumference? It would. Is that essentially just pi times diameter? It is, and that's how you calculate the circumference of a circle, is it not? Okay. All right. Could we calculate the diameter of a circle whose circumference was 41.5? We certainly could. They're giving us the circumference, so they're giving us y and asking us to calculate x. So we would have to go x equals y minus b over m, which is really going circumference divided by pi. That should give us the diameter, yes? Okay, so for these relationships, when you build a graph, there's a mathematical reason that that graph looks the way it does. Okay, this is a relationship that you've known about since you were in junior high. Okay, pi times diameter, or pi times twice the radius. Okay, is how you calculate the circumference of a circle. Okay, any questions about that one? All right, then I would like you guys to do this one here on the rubber band. Okay, so it's called rubber band graph when you go into the Google Sheet. Okay, the rubber band. Okay, get a graph built to that, and then we'll go over a couple of the questions for that. Okay, so does everybody have that graph built? So now, let's see how long, if you can calculate, sorry, how long the rubber band will be if it's stretched with 15 newtons of force. What force is needed to stretch the band to a length of 18.7 centimeters? And how long is the rubber band when it's not stretched? Let's do that one right now, because that actually doesn't require any math. How long is the rubber band when it's not stretched?
6.5 meters.
Centimeters. Centimeters, yeah, 6.5 centimeters. How do I know that? Okay, well, here's how I know it. Remember that equation up at the top, y equals m times x plus b, okay? B is my y-intercept. It's the value of y on this graph, that's length, when x is 0. In other words, there's no force on the rubber band. So that is the unstrained length of the rubber band. It is how long the rubber band is when there's no force trying to stretch it. Okay, everybody follow me there? So our equation for this line is that y equals, okay, 2x plus 6.5. Right? You got to use that equation to solve 1 and 2. Okay, you're either solving for y or solving for x. All you have to figure out is which one. So, for the first one, how long will the rubber band be if stretched with 15 newtons worth of force? Which axis is length on?
The Y.
The y-axis. So they're asking me to solve for y. They gave me a force. That's an x value. So I know x is 15. So that's going to be 15. I already know the other two numbers. So all I have to do is substitute 15 in for x. 2 times 15 plus 6.5 is going to be 36.5. And that's going to be centimeters. All right, everybody okay with that one? Okay, and then for number 2, what force is needed to stretch the rubber band, okay, to a length of 18.7 centimeters? So we're looking for force, which is an x value. We were given a length, which is a y value. So in this one, I know y, m, and b, and I'm looking for x. So I have to manipulate. What do I do to move b? Subtract it. Okay, so I'm going to subtract b from both sides, and I'll have y minus b equals m times x. I want to get x by itself, so what do I do with m? Divide it over to the other side. Okay, now I can plug in my numbers. They told me the length was 18.7 centimeters minus the length of the rubber band when it's not stretched, 6.5 centimeters, divided by m, which is 2. Okay, and the units for that, by the way, are newtons per, are meters per newton. So how much longer it would get per newton of force being applied to it. Okay, centimeters per newton, not meters, centimeters per newton. Okay, so when I plug all that in, okay, I should get 18.7 minus 6.5 divided by 2. All right, so it should use 6.1 newtons worth of force to stretch it to a length of 18.7 centimeters. Okay? Is that making some sense? We're going to work on that some more on Monday. Then we're going to look at position versus time graphs in particular, and then Tuesday we'll do a lab on position time graphs. So, don't forget, your plant projects are due on Monday. Okay, make sure they're done and submitted on Google Classroom by 8:30. Please bring your Chromebooks up here and put them back in the cart.